Hey everyone, I'm Nick, and this is Bytes of Architecture. So in this episode of the series, we're going to be talking about the execution time breakdown of our programs. So in the previous video on Bits of Architecture, we talked about performance. And one of the things we brought up was execution time. So we talked about how our execution time could be broken down into our CPU execution time, so the time that our CPU actively spends working on a program, and then also the time that our program just isn't scheduled on our processor. Then we further looked at how our CPU execution time could be broken down into our user CPU time, so the time spent executing the instructions of our program, and system CPU time, so the time spent in the operating system on behalf of our program, so handling things like memory allocation or I/O. Now, what we're going to be doing in this episode of this series is looking at a number of very simple toy programs here that show off these different areas of execution. So time spent in user space versus time spent in kernel space, which would be our system CPU time, versus times where a program just isn't being scheduled. So let's go ahead and get started, and we'll open up our first example, which will be this 00add.cpp. So we have a very simple program here, and all we're going to do is add 1 to a result inside of a for loop for some large number of iterations. So here, we set the number of iterations right to 2 to the 30. We set up our result as just a volatile int, so it won't get optimized away. And then we just add 1 to our result over and over and over for 2 to the 30 iterations. Right? So let's go ahead and quit out of here, and we'll compile this. So we'll compile 00add.cpp, and we'll do it with, say, -o2 optimizations, and we'll call the output executable, say, add. Now, to get the breakdown of, say, our total execution time and our user time and our system time, we can just run our program with time, right? So I can do time, then /add, and you see our program runs, and we get this nice little breakdown here. And we see that we spend 1.31 seconds in user space, right? So this is our user CPU execution time. We spend roughly 0 seconds in system space, right, or in kernel space. So this is our system CPU execution time. And then 99% of our time was spent on the CPU. So we were scheduled for 99% of the runtime of this program. And our total execution time is this 1.317 seconds here. So you can see here we have a program that is both scheduled almost the entire time, so 99% of the total time of our program was scheduled. And then for most of that time, we spent it in user space, right? So this is our user CPU execution time. Okay, cool. So let's go ahead and get rid of those two things, or rather just the executable here. And we'll go to our next example here, which will be this write.cpp. So we have a bit of a different program here. So instead of just adding 1 to a number constantly, what we're going to be doing is creating this data file and opening and closing it over and over and writing to this file. So a very different kind of program here. Rather than just spending all of our time doing simple arithmetic, we're having a whole bunch of file I/O here. So this is something that's going to require the operating system a lot more. So let's go ahead and quit out of here, and we can go ahead and compile our O1 write, and we'll do it at the same optimization level. And we'll just call our output executable write, and we'll run time write. And we see a very different, overall output here. So you can see that we spend, 0.1 seconds in our user space. So this is our user CPU execution time. But we spend much more time, right, about 3x the time or more, in kernel space, right? So our system CPU time is 0.31 seconds. But we also see that our program actually wasn't scheduled the entire, execution time. So we only spent around 45% of our time actually being scheduled on the CPU. So while our total program took, almost 0.9 seconds to run, we only spent around, 0.41 seconds actively doing any work, either in user space or kernel space. Okay, so here we have a program that's much more dominated by our user CPU time and isn't being scheduled all that much. Okay, so let's go ahead and get rid of this write and this data file that we created. And we'll go to our last example here, which is this o2 sleep.cpp. And this is an incredibly simple program. All it is a main function that tells this thread to sleep for 500 milliseconds, right? So an incredibly simple program. So what do we expect out of this? So let's go ahead and compile o2 sleep.cpp, same optimization level, just for consistency. And we'll call the output sleep, and then we'll run time with our sleep executable. And then after 0.5, or rather 500 milliseconds, our program ends. And what do we see? Well, 0% of our time, or 0 seconds, was spent in user space, 0 seconds was spent in system space, and 0% of our time was actually spent being scheduled. So our program spent basically none of its time actually being scheduled, right? It spent all of its time being not scheduled by our CPU, which is somewhat intuitive. Our program isn't doing anything. All our program does is it runs through what few instructions it has and calls sleep, right? And so the operating system simply sleeps this program until it's done sleeping, and then the program exits. So all of our time is spent not actually being scheduled on the CPU. All right, so those are going to be some 3 very simple examples of programs that are more dominated by, say, your user CPU time versus your system CPU time versus not even being scheduled, and how we can see some of these simple numbers just using time. But that's going to go ahead and do it for today. As always, I'm Nick, and I hope you have a nice day.